Okay, good morning, everyone. I'm Ben Sachs. My company, Sachs & Associates, offers training in C++ for companies all over the world. You'll see the contact information in just a moment. Hope you guys have been enjoying the conference so far. There's a lot to get to, so let's go ahead and just dive in. So the volatile qualifier is something I think a lot of people are aware of in C++, but a lot of people aren't totally clear on exactly what it does. They know it's supposed to offer some protection against compiler optimizations, but exactly what guarantees are supposed to be made and what aren't is not always clear to people. So it's not uncommon to see programmers misapply the volatile keyword, which is a problem because, well, if it just prevented optimizations that you wanted to get, that would be bad enough. But much worse would be thinking that the volatile is offering you some protection that it's not, and then having a very subtle runtime error to debug. So in this session, I'm going to be talking about why volatile is necessary, what protections it provides, how you can understand it when it's placed in object declarations, and then I'm going to close with talking about some possibilities if you think that volatile isn't being handled by your compiler quite correctly. So the classic example of where volatile is necessary is when writing device drivers for hardware devices. So in this case, I'm going to show you an example involving a serial port driver, a UART from the ARM Evaluator 7T. So just to be clear, the device driver is software that communicates with hardware. The hardware may or may not be in the same basic hardware device as the CPU, but it's considered separate. And we communicate with those devices through what are called device registers. And those device registers can do a lot of different things. By writing to a device register, we can do things like configure a hardware device for particular operations, or we can tell it to perform some operation. And that can include things like transmitting data out over a network or over a serial port in this case, receiving data, or just getting general status information. And there are a lot of hardware devices that involve many of these device registers. In this case, the serial port that we're going to be looking at involves 6. Although we're primarily going to be looking at 2 of them, the status register and the transmit buffer, because that's sufficient to explain the real need for volatile here. As is pretty commonly the case in a lot of hardware designs these days, this device uses memory mapped addressing. So the device registers are made to look as if they exist at certain memory locations within what you'd think of as ordinary memory space. Often it's a piece of memory that's separated off from the physical memory space by a little bit here. So this device doesn't have anywhere near the 4 gigabytes that it would have from the full 32-bit address space. But if you were to look at the memory map, you would see something that looks kind of like this, and it's that red area that is the memory mapped registers we'll be focusing on. Really just a small portion of that, but in any case. So diving into the UART directly, let's talk about when you want to write something out, you use both the status register and the transmit buffer register. So there's a bit in the status register, the transmit buffer empty bit, that tells us whether the transmit buffer is ready to use, whether we can go ahead and write something into it. And if that bit isn't set, we shouldn't write anything yet. That generally means that the hardware is still processing the last character we told it to transmit. So we need to wait until that bit gets set to 1. And then we can go ahead and store into the transmit buffer, which automatically clears that bit back to 0, among other things. And the hardware goes off and does its thing. And when it's finished transmitting that character that we just gave it, it'll turn that bit back to 1, and we can then go ahead and give it the next character that we want to write. Now, there are lots of ways that we could access these device registers in memory. In this case, I'm going to be accessing them through references defined like this. So here are the ustat and UTX buff registers for that UART. I've intentionally left volatile out of this declaration here so that we can talk about why it's necessary. I'm going to show you what happens if it's not there. So here is a piece of example code that would go ahead and write a single character out to the transmit buffer. In this case, it loops waiting for the status register to say that the transmit buffer is available. And then once the transmit buffer is available, it can simply go ahead and write the character to that. This kind of busy loop is obviously not ideal. For efficient operation in a larger program, I'd want to be doing something like having an interrupt signal when the transmit buffer becomes available. But for the purposes of explaining why volatile is really necessary, I think that seeing a busy loop like this makes it a little bit more apparent. So the problem here is that the optimizer, based on the declarations I've given it, might wind up failing or causing this code to fail in some way. And I think the problem is a little more apparent if we actually look at a slightly more complex example where I'm actually trying to write two characters, a carriage return and then a line feed. So we wait to write the first character, write it, wait to write the second character, write it. Nothing too terribly complicated. The issue is that although these device registers are sort of being disguised as ordinary memory by the memory mapping approach, they're not really ordinary memory. They don't necessarily behave the way that ordinary memory behaves. When we write to or read from one of these locations, that's meant to have some specific effect on the hardware, what we would call a side effect that would do something like starting it transmitting data out over the serial port. And the compiler doesn't know, if I don't tell it, doesn't know that those side effects are going to exist. And so the compiler's optimizer will do what it tries to do and make my code run faster, which is often a very good thing. But in this case, if it goes ahead and optimizes away some of those register accesses that I'm relying on to tell the device to do what it's supposed to do, my device driver probably isn't going to do what I expected. So in this case, since ustat0 was not declared volatile, the compiler looks at that while condition there, and it can see that the while loop body is empty. So there's nothing in the body of the while loop that's going to change that loop condition, which means either the transmit buffer empty bit is already set, in which case we skip over the loop, or it's not set and the loop goes forever. So the optimizer might transform that into something that looks maybe like this, where it just checks the condition once and then goes into an infinite loop. And this is a more efficient infinite loop than the one we had on the last page. I mean, you can do more no-ops per second if you don't have to keep stopping to check to see, is that bit set? It's kind of silly, but this is the kind of thing that can happen. And so that optimization turns the code into something that looks kind of like this. But that's not necessarily where the optimizer is going to stop, because it can tell that the loop condition on those two if statements, what was the loop condition and what is now just the if condition, is the same. And since the compiler doesn't know that writing to the transmit buffer has any side effect that would affect the value in the status register, it thinks, well, that condition is still going to be the same as it was on the first check. So we can go ahead and eliminate that second check altogether, because Obviously, we're not going to fall into that infinite loop. We would have fallen into the first one instead. So, okay, then we're waiting, we are checking the status bit register, writing one character, and then immediately writing the next. Well, that's a little silly. Why would we ever write something and then immediately overwrite it? Just write the second value and get rid of the first value entirely. And so the compiler might optimize it into something that ultimately looks like this. I mean, it's a much more efficient way of doing the wrong thing. So, in a lot of situations, this is very nice, helpful behavior that the optimizer gives us very nice, helpful behavior, but in this case, it's not doing what we want. So what can we do about this? Well, a lot of tool chains would let us go ahead and disable optimizations for a function or a region of code, and we could go ahead and do that, and that would certainly take care of the problem here. But that might be overkill. There are probably optimizations in here that we would like to keep. I mean, we'd like our accesses to hardware devices to not be unnecessarily slow. Often we're needing to do things to synchronize them, for example. So we don't want to be unnecessarily inefficient here. And so if we disable all optimizations, I think there's a good chance that we'll lose some that we really would have preferred to keep. So Volatile gives us a little bit of a way to get a more targeted solution. So what I should have done earlier would be to declare these two references as references to volatile uint32t's in this situation. And then what the volatile means conceptually, if you think about what the word literally means, it kind of means that the value at that location can change even though the program doesn't obviously do anything to change it. It can change because of reasons that aren't immediately apparent. At a more mechanical level, what it means is the compiler has to assume that accessing a volatile object, which could be reading or writing, reading can have these side effects too, may have some kind of side effect that it's otherwise unaware of. And so the compiler needs to make sure that it doesn't optimize away accesses to volatile objects. So let's talk a little bit about the meaning of volatile as it appears in declarations. Volatile is closely connected to const. They're grouped together as the CV qualifiers in the language standard. So I'm going to be talking about volatile here, but if you're familiar with the rules about what the placement of const means in different situations, you can apply a lot of that to volatile as well. But just to briefly go through this in case you are unfamiliar. So declarations consist of two parts. They're what we call the declaration specifiers in the teal there, and then the declarator in the red. And the declarator is specifying the name being declared with maybe some operators being applied to it that tell us that the thing is something like a pointer or an array. So declaration specifiers, often we think of type specifiers, which can be either keywords like int or unsigned, but they can also be user-defined types like string. But there are also non-type specifiers like extern and static to consider, and I'll talk about the difference there in just a moment. The declarator, as I said, is the name being declared surrounded by operators that make it into the thing being declared being a pointer or a reference or a function or something like that. I'm going to be focusing on object declarations here, but this is true for other declarations as well. So the type specifiers get grouped together, and And that all forms the type of the thing that, in this case, the array is containing pointers to in this situation. Whereas the keyword static is a non-type specifier, so it doesn't group together with the other type specifiers. It really is telling us other information about X besides the type that X has. And what's interesting here is that the order of the declaration specifiers doesn't actually matter to the compiler. I think a lot of us write unsigned long, but if we write long unsigned, it means the same thing. And similarly, whether we write any of those three options down there at the bottom, it means the same thing to the compiler. So we might have standards about what order we write these things in, but that's for our own benefit. That's not for anything the compiler is doing. So volatile, as well as const, is a type specifier, like long and unsigned. So it groups together with the other type specifiers. It is not a non-type specifier that applies directly to the name being declared v. It contributes to the type. So in this case, v is an array of pointers to volatile integers. In this situation, it's the int piece that's volatile, not the pointers themselves. Something that's a little weird about const and volatile is that unlike the other type specifiers, they can also appear in declarators. So they can be both as a type specifier here, and we see in the upper examples off to the left, either volatile int or int volatile means the same thing there. But the volatile can also appear in the declarator to the right of the star in that situation, and then it means something different. Then it's actually the pointer itself that is volatile. It's not a pointer to something that's volatile. The pointers themselves would get the volatile protections. The integers that they point to would not. So that's a possibility. Now, I rarely actually see volatile used in a declarator that way. Almost always when I'm dealing with hardware registers, which is the main reason to use volatile, I'm dealing with that register as something like an integer value or maybe a place to store a character, something like that. I'm sure that there are devices out there that where the value in a hardware register would represent a memory address, but I think they're in the distinct minority. But in case you're ever confused, I think that there's a relatively simple rule for knowing where to place volatile and const in declarations. And it's to first start by writing the declaration as you would without const or volatile. Just get the other pieces in place, and then you can place const or volatile to the immediate right of whatever it is that you want them to modify. This is what typically gets called the east const style, although I guess in this case it would be the east volatile style. So if we wanted X to be an array of n constant pointers to volatile uint32t's, we just start leaving out the const and the volatile, like we see here. And here's the same declaration, but now I'm about to add the CV qualifiers in, so I've left some space for them. So we go ahead and add the const to the immediate right of the star, because it's the pointer part that we want to be constant. These pointers should always point to the same locations, since it's an array. And those locations, the values at those locations, should be treated as volatile. So we put the volatile to the immediate right of the uint32t. Certainly there are other approaches to writing this, but I tend to think that this is a relatively nice, simple example. If your coding standards say to do something different, I understand. But I think that regardless, keeping this in the back of your mind is something that can be helpful for keeping track of what const and volatile mean in different situations. All right. So what protections does volatile actually provide? Well, I mentioned before that the compiler has to assume that accessing a volatile object, again, reading or writing, can have a side effect. And the compiler has to assume, moreover, that the side effects from accessing volatile objects might be related, because the people who developed the rules for volatile and for the compilers knew that there might be multiple registers involved in operating on a hardware device. And so the compiler needs, just from the fact that these are volatile, notice there's nothing in these declarations that makes it clear that there's any kind of connection between ustat0 and utxbuff0. Nothing that says that writing to the transmit buffer can actually affect the value in the status register. But the compiler has to infer that from the fact that those two values are declared to be volatile. So from that, it has to conclude, for example, that it can't reorder this code in any way. That even though there's no obvious connection between the transmit buffer and the status register, it can't, for example, move the right of the carriage return character above the check on the status register, because the programmer is relying on the fact that volatile operations like that won't be reordered. Or at least the programmer might be relying on that, and the compiler doesn't have any other information it can use to say otherwise. So I mentioned volatile disables optimizations for a specific object, not a region of code. And so when you declare one object in a block of code to be volatile, there are often other volatile objects that exist in that same block of code that are being accessed around it. And while, as I just mentioned, the compiler won't reorganize accesses to volatile objects, it is actually permitted to move accesses to non-volatile objects around an access to a volatile object, either before or after. And this is one of the main reasons why, although historically volatile was sometimes mentioned as a tool for inter-thread communication, it's really not a reliable way of doing that. So, in a paper they wrote in 2008, Eric Eide and John Reger, I apologize if I'm mispronouncing those names. I believe I got them right. Presented this example where they showed someone was writing this code expecting that the intent was that the buffer init function would clear out a buffer to get ready for some other piece of code to use it, and then set the buffer ready flag, which, because that was volatile, that was meant to be something that another thread would see as a potential change. If someone was in another thread looping, checking to see when does buffer ready become true, that value would change at some point, and we would expect that that loop would then terminate, and then they could go on and use the buffer safely. But in fact, that's not the case with these declarations, because in fact, since it's just the buffer ready object that's volatile and not the buffer itself, the compiler might consider moving the right to buffer ready before the loop. Or if you prefer, it might consider moving the loop after the write to buffer ready. It's 6 of one, half dozen of the other. Either way, the signal would then arrive before the buffer is actually meant to be ready. So if they wanted to actually use volatile for this purpose, you'd need to make both objects volatile in this case, which would at least prevent the compiler from reordering things. But it would also, of course, prevent any optimizations involving the use of values in the buffer, which is quite probably not what we wanted to have be the case. So volatile is really not intended for multi-thread communication. The standard library and other threading libraries now provide synchronization tools that are really designed for inter-thread communication, and you should be using those instead of using volatile. Volatile is really intended for accessing things like hardware devices. So another important point to note is that volatile doesn't make accesses to the object atomic. It is possible to get a data race when you are accessing a volatile object because that access is not atomic. So for example, here, suppose this code modify value is running on a thread A here. And we're going to assume for the moment that double operations are not atomic on this platform. If we execute line 1 there, and then start executing line 2, since that's not an atomic operation, another thread could potentially come in and look at the value in V, while line 2 is somewhere in the middle of doing what it's trying to do. And then they would see a value that was neither 8.67 nor 53.09. They might see half of the write being finished, for example. And in particular, operations like these, the increment and decrement operations, as well as the compound assignment operations. These are specifically not guaranteed to be volatile for, not guaranteed to be atomic for volatile objects. Although there's language in the standard that says things like V plus equals 3 evaluates V only once. That's for the sake of locating where V is. It doesn't actually change the fact that that V plus equals 3 has to involve one read and one write to that location. Okay. So, Eric Ide and John Reger also were the paper that I was citing earlier. They were testing for compiler bugs. This is something that Reger had actually noticed in, I guess while he was teaching a class. He discovered in class a compiler bug involving volatile. And so what they were trying to do, the title of the paper was Volatiles Are Miscompiled and What to Do About It. And so this paper was obviously written some time ago, 2008. But it is something that is, I think, still a concern. You can find videos of John Reger talking about compiler bugs related to optimization. Well, the most recent one I found was from December of last year, but that's not necessarily the most recent. But it gives you some idea of the notion that this is still a concern, potentially. And what they found at the time was that of the 13, compiler tool chains that they tried, they were looking at primarily versions of GCC, but they had some other compilers that they were looking at as well. They found that all 13 of the compilers that they looked at produced incorrect code for at least one usage of volatile. Now, they were using randomly generated test programs. So if you go and look at their paper, the programs don't necessarily have a lot of obvious meaning. And they try to be careful there to say that these are issues inside the compiler. It's hard to predict whether any of the individual bugs that were noticed would really result in failure, in real-world failures in practical applications. But I think it's something to be concerned about, because often we're writing hardware devices that are meant to operate in safety-critical environments, situations where someone's life could be at stake. If something happens to misbehave, that could be a real serious consequence. As I said, these specific bugs were found a while ago, and they actually mentioned in their paper that they'd been able to get 2 of those bugs fixed by the time by submitting them to the compiler authors. They didn't go in and do that themselves. They'd managed to get 2 of those fixed even by the time the paper was presented. But they also mentioned that it's probably something that we should expect is going to be an ongoing problem, because compiler writers are often looking to improve their optimizers. Optimizers are one of the big selling points of a compiler, in a sense. You don't want to be the compiler that's delivering noticeably slower code than all of your competitors. So as optimizers improve, that's in a sense fighting against the protections that Volatile is supposed to provide. And so this is something that could easily be, it's probably something we need to continue to be concerned about going into the future. So if you suspect that your compiler is actually mishandling a volatile object, what can you do? Well, one thing to do would be to turn off optimizations for the affected code. So here, for example, if you were using GCC, the attribute GNU optimize lets you specify an optimization level for a function to be used instead of whatever optimization level the compiler is using by default for the rest of the code. And in this case, this would set the optimization level to 0, which means, well, minimal optimizations should be performed. They're actually careful in the documentation to not say that there are no optimizations that would be performed, but they refer to it as minimal optimizations. And when I've taken efforts to compile things like this, I did see a pretty noticeable difference between O0 and, for example, O1. Alternatively, there are other ways using, say, pragmas that a lot of compilers have for disabling optimizations. Here's, again, some code that would work in GCC for essentially changing the optimization level for a block of code and then re-enabling the previous optimization level before. Different compilers do this in different ways because pragmas are not a standard part of the language. Each compiler implements their own, but this gives you some idea of where you would go to look to find information about how to disable optimizations. I believe this one also has to be done on a function level. If I tried to put this inside the body of the function, I don't believe it would work. Another approach you could try would be to use a different version of your compiler. Or, if you want to go to an extreme level, a different version of the compiler altogether, or a different compiler altogether, although that's probably a much larger undertaking. As I mentioned, ID and Reger tested a number of different compilers, including several versions of GCC in this situation, and they found some fairly significant differences in terms of how many volatile bugs they noticed in each of those compilers. And one particular note that's important here is that it wasn't necessarily the more recent compiler versions that had fewer volatile bugs. For example, they actually found that GCC 4.2.4 had more volatile bugs in it than 4.0.4, which they speculated to be because GCC 4.0 had been a fairly significant reworking of some systems, and so they needed to take things out of the optimizer to make sure everything was working initially, and then they could go ahead and start, once they knew that the code was working, that the compiler was doing what it should do in most circumstances, they could go back and try and optimize more. But of course, in situations involving volatile, that's pushing the envelope in ways that might create problems. And by the way, I'm not trying to denigrate the compiler writers at all here. I think they have a very, very difficult job, and they get it right so often that we should probably all be really impressed at their level of success. But they are, in a sense, between a rock and a hard place here. So we should be understanding of the kinds of situations that they face. ID and Reger also provided a workaround in their paper that they found solved most of the issues that they encountered. And specifically, it involved accessing the volatile object through non-inline functions. So what they did was they created two versions for each type of volatile, two functions for each type of volatile object that they were going to interact with, one for reading and one for writing. So if this is a typical piece of code that reads from a volatile integer, here is that same code with their workaround applied. They actually used a C version of the functions, but here I've presented a C++ version. And I compared this to the code that was literally in their paper, and it produced the same result when the generated code turned out to be identical in the tests that I ran. So, yeah, it's a fairly simple function. It really just wraps around reading a volatile object. But if it's not inlined, it does the job. And similarly, if you wanted to write to a volatile integer, typically you would write the code something like this. If you were using their workaround function, it might look something like this instead. Again, this is a C++ version of what they'd written. Now, why does this help? Well, I mean, it's hard to say for sure. They were clear. They were only speculating in their paper. But a call to an inline function, the compiler can't see through that. The compiler really doesn't know what the function is going to do when it's executed, or what side effects might occur as a result of executing that function. And so, if the compiler doesn't know exactly what the function is going to do, it better call the function the number of times that the programmer wanted the function called. If it tried to optimize away calls to a function that it doesn't know what those do, what those calls do, it could easily produce some incorrect behavior, which is pretty similar to the behavior that we expect from volatile objects. Again, the compiler there, it can't be sure about what's supposed to happen when it accesses a volatile object. So it has to follow our instructions more rigorously than it ordinarily would. And so in this situation, the non-inline function provides a kind of redundant backup for the level of protection that volatile is supposed to be providing here and wasn't in the examples that they were looking at. So if we were to look at the UART code, the serial port code that I had earlier, using these workarounds, here are a couple of versions of the function designed for uint32t's. And here is the code for those, for the status and transmit buffer registers from before. You can see down there in the red the places where I've added in calls to these workaround functions to try to avoid any problems that could be caused by a miscompiled volatile. I wasn't actually seeing a miscompiled volatile in my use of this hardware. So when I tested this, I was looking at the generated code and making sure that it really was generating calls to these functions that were truly opaque calls. Which, by the way, I did consider making these functions into templates, since they had different versions of these functions for each different type of variable that they wanted to interact with. And that's, since they look exactly the same, seems like a good candidate for making these functions into templates. But of course, when we make something a template, we have to put the implementation, the body of the function, into the header file. And when I tested that with GCC 10, I found that at anything other than optimization level 0, the compiler was inlining these functions, even though I hadn't specifically used the keyword inline. It could see the bodies, and so it went ahead and substituted them inline anyway, doing me what it thought was a favor. So I found that I could work around that by tagging those two functions with the GNU NoInline attribute. And in that case, this really did produce the same code that I was seeing with the non-template versions of those functions from back here. But it's something that you want to watch out for. So if you decide to try and use template versions of these workaround functions, do make sure that they are not being inlined away. Okay. So volatile, big takeaways here. Volatile tells the compiler that accessing an object might have side effects that shouldn't be optimized away. And so the compiler needs to treat accesses to that object more literally. The compiler isn't allowed to reorder accesses to volatile objects, because accessing two volatile objects, they might be part of the same underlying hardware device, and those interactions are meant to be in some way related. But reordering accesses to non-volatile objects around volatile accesses, that is permitted, and that can create problems in certain situations. In particular, as I mentioned, that's one of the reasons why volatile is not really a reliable mechanism for inter-thread communication. Instead, we want to be using things like mutexes, semaphores, condition variables. Those are really tools that are designed for inter-thread communication. Volatile is not really intended to work that way. And accesses to volatile objects are not guaranteed to be atomic, so we shouldn't rely on that behavior. And if you do happen to find that your compiler is mishandling volatile, here are some things you might try. You might try disabling optimizations for the affected code, using a different version of the compiler, or employing the workaround that ID and Reger demonstrated. If you are going to do that, make sure that the functions aren't actually being inlined for you, because of course that will defeat the purpose of the workaround. Okay, that brings us to the end of the talk. I'm happy to take any questions you guys have at this point. Yeah. So, is there a microphone? I think we can. If you would please come up and use the mic, or unless we have one that we can pass around. Okay.
So, for the reordering thing, I'm surprised that you didn't mention using memory barriers or what we have in C++ as like synchronization points.
Oh.
Which is how we do that a lot.
Yes.
Right?
Yes, you certainly can. If you were interested in using working at a low level, yes. Typically, what you would put in to prevent the kind of the question was about using memory barriers, and yeah, if the where was it? If you are seeing the compiler reorganize your code like this, yes, there are memory barriers that we can go ahead, that's what they're typically called, to tell the compiler that it can't reorganize, move code across one of those barriers in that situation. Yeah, I encouraged the use of things like semaphores and mutexes because my understanding from talking to people who do a lot of inter-thread communication is that using those high-level tools tends to be more reliable and suitable for a lot of applications. Using a memory barrier would be appropriate. It would work, I think, but it's often operating at a lower level than I think a lot of applications would typically operate.
We typically use them a lot to prevent these kind of optimization issues rather than like sort of
yes.
like higher level synchronization issues.
Okay. Yeah, I mean, if you're using memory barriers for that purpose, usually things like mutexes and semaphores, they have those memory barriers built in or some equivalent. So yeah, if you're using explicit memory barriers, I think that's perfectly fine. And yeah, if it seems to be working for you, great, go ahead and do that. I was just focusing on, I wasn't really thinking about this too much as a talk for inter-thread communication, so I didn't want to get too far down into that. And yeah.
All right, thank you.
Mm-hmm. Yeah.
When you were discussing how Volatile does not guarantee atomicity of things like compound assignments, I would like to point out that because of that and because that's so surprising, C++ 20 deprecated most of those uses of Volatile. I think everything on this, all of those on this page, the increment, the decrement, and the compound assignments, I believe those are all
right. Yes, it's true that they are now, that these operations, well, some of them were deprecated in 20 and then undeprecated in 23, I believe, because the problem was, well, people had code in the field that they said that they took that to be, when the compiler started complaining that these things were deprecated, they took that as evidence that C++ doesn't know what the hell it's talking about. Obviously, I should be using C instead because, yeah, and you can go and you can find Reddit threads that were major conversations. And I mean, I think that they were not getting the protections that they thought they were getting. And so when some of this was undeprecated, and most of it is still deprecated from what I understand, but when some pieces of this were marked that way, they were marked, as I understand, with specific statements to say, by the way, just so you're clear, no atomicity here. These are not atomic things, but yeah, I think so. Depending on what version you're compiling as, I think that, yeah, you might see different things labeled as deprecated, depending on what exact version you're using. But yeah, did you have a follow-up question there?
No, that's it. Thank you very much.
Yeah, thank you.
So if volatile is used to allow the compiler or tell the compiler that the value can change, can I put a constant in there to say prevent me from changing it or future developers?
Yes, there are occasionally reasons to have objects that are both const and volatile.
Okay.
Yes. I didn't show it here in this example, but in the larger body of code from which the examples involving the serial port driver were drawn, I eventually make the status register into a constant volatile object because I'm really not intending to write into the status register. It's really intended only for reading purposes. But yeah, it does make sense that you should be able to prevent yourself from making those sorts of mistakes. And from what I understand, the tool chains generally support that pretty well. I believe that the language in the standard is a little odd about exactly what it is, but I believe, as far as I know, all implementations of it essentially do the right thing and allow you to create a const volatile object. Yeah. You guys can just come up and form a line behind the mic, by the way. You don't have to raise your hand and have me call on you individually.
I was just wondering that how does this tie up with out-of-order execution in a way that, is it enough to just ensure that the compiler is not reordering things?
I'm not sure what you mean when you say how does it.
So modern hardwares would have CP pipeline which does out-of-order execution, right?
Mm-hmm.
Depending on tracking dependencies.
Mm-hmm.
So even if we are able to somehow avoid the compiler not to reorder non-volatile code versus volatile code,
Mm-hmm.
doesn't out-of-order execution come into play in the hardware?
That's again solved by a memory barrier.
Yeah, exactly.
Yeah. Yeah, I mean, it's true that, yes, out-of-order execution and things like pipelining, yeah, I believe they can be concerns here. And in fact, one of the things that I didn't mention, but maybe I should have been clearer about, was that the side effect, I said that accessing a volatile object can have side effects. The side effect from the point of view of the compiler is considered complete once it's executed that line of code. In the example that I was giving, writing to the transmit buffer initiated a hardware operation that was then going to take a little bit of time to actually complete. Yeah, the compiler doesn't know about that. And yeah, there are certainly issues that can come up with the kind of thing that I think you're describing there. Again, yes, as David mentioned, the using memory barriers in those situations, I think, would be appropriate for solving that problem. Okay, maybe I should have given more emphasis to that, but
I just have another question, if it's
yes.
okay. We had a code base in our firm wherein we tried to use volatile as a way of prefetching.
Prefetching.
Yep. So we wanted to do some level of cache warming. So we used volatile to do a prefetch of the memory. So it was otherwise, if it was not a volatile, the compiler would have just removed that code as dead code. But using a volatile, our idea was that maybe we can still force the execution to fetch those cache lines. So I was just wondering, is that what are your thoughts on like prefetching and volatile? Any ideas?
I mean, my thought would be, I think I would look for other ways of accomplishing the goal first.
Okay.
I can see how you guys would come to the conclusion, and yeah, maybe depending on what I was able to come up with, I can see why that might seem like a good solution. I think what I would tend to look at first off for what you're describing, you're specifically talking about cache lines. I believe that there are added in 17, I think, there were these symbols, hardware constructive interference size and hardware destructive interference size, that I think I would first look at taking advantage of those. Those are meant to give you a sense of how far apart objects need to be on different cache lines, or alternatively, how close together they need to be on the same cache line. And I believe that if you look at example code featuring those, I think that's where I would look first for information about how to do cache prefetching the way that I think you're describing.
Okay, thank you.
I'm just trying to answer that question, actually. Look into prefetch intrinsic or the prefetch instruction. They're specifically doing that.
Okay, so my questions go back to slide 45.
Yeah.
If I declare the child buffer also to be volatile, will that help?
Yeah. Oh, yes. So in this situation, yeah, if you declare the buffer to be volatile here, then yeah, the compiler would refuse to reorder the buffer register, or the buffer ready assignment before any of the operations on the now volatile buffer itself. Yes, I expect that would be the case. But that, of course, has other knock-on effects with regard to how I would be able to use the buffer in other situations. Yeah.
Hi. So 2 questions.
Yeah.
Number 1, you keep mentioning volatile objects. The only real-life use that I've seen for volatile is registers. Are there other use cases for classes or whatnot? Second question, I saw that you used the attribute GNU NoInline as opposed to the keyword NoInline. I was wondering why.
Oh, I have to admit, I don't think I'm familiar with NoInline as a keyword. That's I think that was just when I did some searching for how to accomplish that goal. What the appropriate options were for preventing inlining. That was what came up.
Where it is a keyword, no inline.
Okay.
It's the Microsoft compiler's version of it.
Okay. Yeah. Thank you. Yeah. With regard to your other question, I'm sorry, I got those out of order. What was the other topic?
Volatile objects.
Oh, yes. Yeah, as things other than device registers. Device registers are certainly the classic example, and they're the one that is used inside the standard as a description of why you might want to do something like this. Now, the standard is very careful to not to say that these things absolutely have to be used for dealing with hardware devices. They leave open the possibility for other objects for other reasons why the kinds of protections that Volatile provides might be useful in other situations. But I think that what experience has shown is that often there are other tools like thread synchronization pieces or memory barriers that are more appropriate to the task at hand than Volatile naturally is. So I think while there certainly may be other uses for it, I would want to carefully consider my options before using Volatile in a different situation. Yeah. I think that brings us to the end of our time. So thank you all for coming. Hope you guys enjoy the rest of the conference. Good luck to you.